Okay, our next section, 9.3, will carry over on our discussion with exponential growth and exponential decay. We will actually be talking more about continuous growth and decay, which is slightly different, but very much related. So take a look at our learning goals. We want to recognize the properties of exponential functions, allow these exponential growth and decay models to work, and then again, graphs. So as I said, very similar, but different in a little regard. So if you start looking at some of the compoundings we've been doing, specifically with money, you should be able to take any amount of money, put it in our compounding formula, which you can see up there at the top, A equals P times 1 plus R over N to the power of NT. So our compounding formula, and see what happens to that money. Now, if we do something very simple, and this is where I want you to look at it, we're going to do this in class and show where the numbers come from, but we're only going to take $1. And if we take $1 and if we take 100% interest, give you 100% interest, 100% return on your money, which is what with banks not do at all. It would be a great return. And we're going to do that for 1 year, and we're going to see what that turns into. So most people say that, hey, our $1 should turn into $2. But since we have this compound interest thing, and we know with the more compoundings, the better return you get, we want you to look at this. We're going to break up into groups in class and figure this out and look at these numbers. Now, you got to think quarterly, the bank does pay. Monthly, a lot of things happen monthly. The bank usually won't give us any interest for weekly, daily, any of these. Hourly, by the minute, by the second. But what if we can even go faster than that? And you know we can. There's things in technology, nanosecond, millisecond, all those different combinations. So, long story short, we'll fill this chart out in class and we'll notice something. But in the meantime, introduce you to what we call the number E. And it is truly a number. If you look at your calculator very carefully, you should find a couple different places for it. There's an E key by itself. I'm not talking the alphabetical character. Then there's, I believe on most of your calculators, it's an E to the X key. And I think those are the two most of you are going to have. The E to the X you should find over by the squaring key, just a couple down from it. And it's not right on the key, it's above it, so you have to hit second, then that key. And the E key is right above the divide key if you're working with TI-84s. Okay. So if you hit that on your calculator, second divide, you should be able to see this number. And 2.7182818828, it keeps going, but it doesn't repeat really, even though some of you can say, well, it looks like it's 18281828, but it's actually rounded at that last digit, so it's really not repeating. So this is going to be called our continuous growth and decay factor. Okay, and we've been using our y equals ab to the x, and we called b our growth factor. So instead of a b, we're going to have an e in that particular spot in our equation. And what's going to make it different, it will no longer say compounded quarterly or anything like that. It'll say continuously compounded. So if we could turn this thing over as fast as we possibly can and get interest, that's what we're really doing. So moving forward, that then means if the E becomes a B, the B becomes an E, we're going to have a slight little difference in our work. So we have a new formula. I like to call it Pert because it does spell out the word Pert. It's just A equals P times E, same level, and then to the power of RT. So we have our rate in there, we have our time, we have our original amount of money, and we have that E value, which is that continuous compounding number we just talked about. Now, in the book, they talk about PERT being called the continuous compounding interest formula, because usually that's the one you deal with money on. The continuous change model deals more with like populations, species of different animals, insects, microorganisms, etc. So if you look at these three formulas, I'm trying to parallel with the use of color here, why they're or how they're equal. So the answers, depending on which formula you look at, are all in the same spot. The result of the calculation, the answer. Then you have your initial value, your y-intercept, we called it, and that's still there. So we could add those to our work, our y-intercept. We said original value, so initial value is the same thing. Okay. The growth factor always grew before, and it was greater than 0, it grew. If it was less than 0, it didn't. Now the growth factor is that E value, and E is a number. And then the time interval is usually time in years, but in ours, we're going to have the time interval and the interest rate. And remember, the interest rate must be written in decimal form. So that's really the only differences you're going to see. So PERT and NERT, they're really the same equation. If you go back and look at them, we could do it with a population. We could do it with money. So if I said we have $3,000 compounded continuously at a rate of 5% for a total of 5 years. So that would now be our formula. We would grab our calculator, because again, most of you aren't going to do calculations with 3,000 in your head. So $3,000 compounded continuously. Here's where you'd probably want to use the e to the x key. So over on the other side, second, on my calculator, it's second ln. So e to the x, and then you put a parenthesis down, 0.05 times 5, close the parenthesis, and we are getting a nice return on our money after just 5 years. We've got $3,852.08. So our money really grew by almost $1,000, $850-ish on our return. So good job. You're going to use this the same way. It will have to say continuously compounded if you now have the idea or the formula where you have to use PERT or NERT, the E value. Okay? So that's all for now. Let's try a couple problems and see where your questions are.